All right, friends, welcome back. In this video, I'd like to go ahead and start Chapter 4, which is going to discuss rational functions. And you can see here that Chapter 4 is going to be pretty short for us. We're only going to do a quick quiz over this chapter, only 2 sections long. So in this video, we're specifically going to talk about Section 4.1 and talk about what rational functions are and also this idea of asymptotes. And then in the next video, in 4.2, we're going to talk about how to graph rational functions and how to analyze graphs of rational functions. So let's get started with that, with Section 4.1 here, again, talking about what a rational function is. Well, a rational function, we already talked about what a rational expression is earlier in the year, and we said that it is basically just a fraction of polynomials. Your numerator is a polynomial, and then separately your denominator is a polynomial. So a rational function is simply just a function whose function formula is represented by a rational expression. And so we are going to talk about a numerator and a denominator, both of which will look like polynomials here in these exercises. And just a couple of things just to kind of make sure that we know what we're talking about here. Because we do have a denominator, one of the things we're going to need to remember is that the denominator is never allowed to equal 0, okay? So because it's going to be a polynomial, we might be interested in the zeros of that polynomial because those would be the inputs that make the denominator equal to 0, and we can't have that, okay? So we'll see what that's going to mean here for us here in a little bit. It says here that the numerator and denominator have no common factors, so if they are polynomials and they do factor, then maybe they have some common factors that would cancel out, and we would just be interested in that final product after canceling. And then it says here the domain includes all the real numbers except for the x values that make the denominator equal to 0, which makes sense because we cannot have the denominator equal 0. We're going to have to exclude the ones that do make the denominator equal to 0, okay? So as the most basic rational function, we could take a look at f of x is equal to 1 over x. And again, the unique thing about this is your input is in the denominator, okay? So whatever the input is, this machine is going to take 1 divided by that number. And so it's going to create a graph that looks a little bit interesting, maybe is a shape that you have seen before, or maybe you haven't seen before. It's very different from a lot of the other shapes of graphs that we've talked about this year so far. And this actually has a name. It's called a hyperbola, okay? And so this comes up a couple of different times throughout the course of high school mathematics, and so we give it a name to stress the importance of it. And what I want to do is kind of talk about the relationship between input and output, right? So we've taken a look at this sort of thing before about end behavior, okay? So you notice here that with your hyperbola, we actually have a couple of different ends, right? So we have these two ends right here and here, and then we have, of course, the ends here and here, okay? And so 4 different ends to this curve, it's a little bit interesting or a little bit of an issue to try to figure out how you would describe that sort of thing. But the way we always describe end behavior is we talk about what the outputs are doing as the inputs go further to the left or further to the right, okay? So what if we were to discuss that, right? So if the x's were approaching further and further to the left. The way that we would represent that is we'd be saying the x's approach negative infinity, right? So they go from -1 to -2 to -3, et cetera, in that direction. Well, you notice what the end of this graph is doing as our x's approach negative infinity. Your y values here along the curve are just going to correspond to places along the y-axis in this way. And you notice what we are approaching, okay? So as your x's get further to the left, you'll notice that your outputs here are going to constantly approach this value of 0, okay? So f of x, the output, would approach 0 in this way, okay? So it'll approach 0 from the bottom. You notice that as your x's get further to the right, as we might say x approaches positive infinity, so x is 1, x is 2, and 3 and 4, etc., you'll notice that we are talking about this end, and you'll notice that if we talk about all the points that are on the curve there, those all correspond to y values that would be here, and of course that would be, your y values would be approaching 0 from the top, okay? And so we might say there f of x is approaching 0 again. So what you're going to notice here, and how we're going to describe this, is that you have this boundary line right here at x is equal to, or sorry, not x, at f of x is equal to 0, or in other words, y is equal to 0, right? We call this sort of thing a horizontal asymptote because that is a boundary line that my path of my graph, my end behavior, will get closer and closer and closer and closer to as the x's go further to the left and to the right, but we are never actually going to touch or cross this imaginary boundary line with our ends of our curve in this way, okay? And so you'll also notice here that if we go ahead and reverse some directions, we can go ahead and have some other discussions here. So let's go ahead and reverse the directions of where we're going. Maybe let's say that from the left, we approach inward, okay? So as our x's approach inward like that, what is our y's doing, okay? Well, you notice that we are now talking about all of these outputs along the curve here, and those all correspond to outputs that are approaching negative infinity, okay? So it's all about describing what your outputs are doing as your inputs are going further to the left or further to the right, okay? If we go ahead and approach with our inputs from the right, then you'll notice that we're talking about this end behavior, and you'll notice that that is going to be going up. So f of x is going to be approaching positive infinity, okay? And so to just kind of organize a little bit of that data here, we might go ahead and summarize it using this, right? So again, this is all to say that when you talk about a hyperbola, you are going to have these imaginary boundary lines that your end behavior of your graph is never going to touch or cross. And again, that all has to do with the fact that in the function formula, you are dividing by the input, okay? And so, of course, 0 would be a problem to plug into this machine. That's why we have all these imaginary boundary lines at 0, okay? And so, again, this brings up this whole idea asymptotes, which again basically are these imaginary boundary lines, either horizontal or vertical, that the end behavior of your curve is going to infinitely approach, but it's never going to intersect or cross these boundary lines, okay? And we describe that using the same method of describing end behavior that we've seen for other functions in the past. Now, one of the things that you're going to be asked to do is actually go through and find your horizontal and vertical asymptotes. And so just a little bit of an explanation about how to do that here, right? You might have a function, again, a rational function that looks like your output is equal to a numerator polynomial divided by a denominator polynomial, right? So n of x over d of x, okay? And again, we all remember what a polynomial looks like, but just in general, again, what a polynomial looks like is it is an algebraic expression with some sort of number in front of x. Again, we call that a coefficient, times x raised to some power. And remember that if it's the standard form, the exponents on x descend as you read from left to right, okay? And so let's just say that I'm dealing with a rational function that looks like this, a polynomial over a polynomial, okay? Well, it says right here, the graph has vertical asymptotes at the zeros of your denominator, okay? And so whenever you guys are looking at a rational expression or a rational function, you're going to have to take whatever the denominator is, and you're going to have to set it equal to 0 in order to find those problem values, okay? Because we know that the denominator is never allowed to be equal to 0. If we're able to find those problem values, then we know exactly where our boundary lines are going to be. Those are going to be the places where my graph will get very, very close, but it'll never touch it or cross it. If we did touch it or cross it, then we would be equaling 0 at those boundary lines, and we can never do that with our denominator. And then it says, find the vertical asymptotes. You simply just, again, set the denominator equal to 0 and you solve. For your asymptotes, it turns out that it's not quite so straightforward. It's going to depend on the characteristics of your rational function here. So specifically what you guys need to look at whenever you're figuring this out is going to be the degree of the polynomial that's on top and then the degree of the polynomial that's on bottom. So the degree, remember, is just the largest exponent of the polynomials on top and the bottom. You're going to need to compare them and see if they are the same number or if one is larger than the other. You're going to have some different conclusions based on what you're going to have, right? So in the case where you have the numerator has a smaller degree than the denominator, right? So in the case where you might say n is less than m, I call this being bottom heavy, right? Because if m is the greater number, then of course I'm heavier on the bottom than I am in the top. Okay, so if you are bottom heavy, then what you can automatically conclude is that you're going to have an automatic horizontal asymptote of the x-axis or the line y is equal to 0. Remember, that would be what you might consider to be a HOI from a previous algebra class. Okay, so that's just automatic, right? So if you determine your function is bottom heavy, you're going to automatically conclude that, okay? Another really easy comparison is if it's top heavy, right? So if the degree of the top is more than the degree on the bottom, right? In this case, your conclusion very simply is that you don't have any horizontal asymptotes, okay? So if you are top heavy, then we don't have any horizontal asymptotes to speak of, and that's another really easy conclusion, right? Of course, the only final case there is what happens when the degrees are, of course, equal to each other. So if you find the degrees are equal, then what you need to look at are the coefficients of your leading terms here, right? So you need to take a look at the fraction a sub n over b sub m. Whatever this fraction is right here, that is going to have to be something that you take a look at and figure out what that number is, okay? So I'll say that down here, right? So it says if you have equal degrees, then your horizontal asymptote is basically going to be equal to that fraction or that number, okay? So you basically just take a look at your leading coefficients, you put them in a fraction and reduce it, and that is simply going to be your horizontal asymptote, very simply, right? So while we do kind of have to split it up into cases like this, it's pretty easy to remember, right? If you're bottom heavy, it's the x-axis that's your horizontal asymptote. If you're top heavy, you don't have any horizontal asymptotes. And of course, if it's equal degrees on the top and the bottom, then you have an automatic horizontal asymptote at the ratio of the leading coefficients here. So let's take a look at a couple of examples where we're actually finding those, right? And so again, we need to find both vertical asymptotes and horizontal asymptotes. And so down here, I'm going to make some places to go and kind of show my work. So vertical asymptotes and horizontal asymptotes, VA and HA. And we said to do this first, we want to take a look at the denominator, which it looks like here is just going to be x is equal to 2. And we simply just want to go ahead and set this equal to 0 and solve. Okay, if we do that, then what we're going to be finding are those problem values where the denominator is going to actually end up being equal to 0. We know that we can never have that, so that's going to correspond to a vertical asymptote in this case, right? So it looks like the polynomial on bottom simply is just x plus 2. If we set that equal to 0 and solve, we simply get x is equal to -2, and that represents our vertical asymptote in this picture, right? So if we were to draw a quick sketch, we just go ahead and draw my y-axis and my x-axis. I would simply just go over to the left 1, 2, and I would drop my imaginary boundary line right there. Okay, so that would be a place where my function is never allowed to touch or cross in its end behavior. Okay, if we were to go ahead and take a look at the horizontal asymptotes, again, we would just need to simply take a look at the degree of the top and the degree of the denominator. Okay, so the degree on the top, of course, is 2. The degree on the bottom, of course, is 1. And we notice that this is an example that is top heavy. And so what we will automatically conclude is that we do not have any horizontal asymptotes here, okay? So again, if it's top heavy, that's going to be an automatic conclusion that you can make. So the only boundary line that we're going to have in an example like this would be that vertical one at x is equal to -2. To save time in the video, I've already done example 3. I invite you to go ahead and pause the video and go ahead and read this yourself to just try to make sure that this makes sense. And again, in this one, you're going to have to take the denominator and set it equal to 0. That turns out to be a quadratic, which you can see that we just go ahead and factor and then get our two vertical asymptotes in this way. And then, of course, this one is bottom heavy, so we have an automatic horizontal asymptote at the line y is equal to 0. Okay, let's do this next example together. So example 4, we have another one here, and again, just going ahead and taking a look, we just need to go ahead and find our vertical asymptotes first, and then go through and find our horizontal asymptotes. And so to find our verticals, we just go through and we go ahead and set the denominator equal to 0, and we solve. So here the denominator is represented by 3x squared minus 3. We set that equal to 0 and we solve. So this is a polynomial equals 0. What we would always want to go ahead and check to make sure to do is see if this factors, and I think that this definitely does. So we could factor out a GCF of 3, leaving behind x squared minus 1. And then we can go ahead and notice that that x squared minus 1 is a difference of 2 squares, so 3 times x plus 1, x minus 1. And then use zero product property to get our two values of x here, right? So x is going to be equal to -1 and x is equal to +1. These represent our two vertical asymptotes here in this example, okay? So again, if we were to draw a quick picture of this, y-axis, x-axis, we would go to the left one and put one of our boundary lines there. Go to the right one, put one of our boundary lines right there. Okay, so again, these would be boundary lines that my graph can never touch or cross in its end behavior, okay? For the top and the bottom, you notice that the degree on top is simply going to be a 2. The degree on bottom is simply going to be a 2. So that is equal degrees. So the degree of n of x is equal to the degree, if I can spell, the degree of the denominator d of x. That's because 2 is equal to 2. And so we will automatically conclude here that the only horizontal asymptote that we're going to have is going to simply be the ratio of the leading coefficients here. And so the leading coefficient on top is 2, the leading coefficient on bottom is simply 3, so the ratio of those two numbers is 2 to 3, or in other words, the fraction 2/3. Okay? So in my picture, I would just simply have to go up 2/3, and then that is where I would horizontal boundary line, and then go ahead and draw the rest of the picture in that way. Okay? So again, we're going to take a look more at graphs in the next video. So here we're just trying to get a feel for how to go ahead and find these characteristics of graphs here first. Example 5, I invite you to go ahead and pause the video to see if you could give this a try on your own. The only thing that I'll remind you about is that when you look at the polynomial in the numerator and the denominator, you just want to make sure that they're written in standard form. And so this one right here would have to be one that you rewrite in standard form just to make sure that you don't forget to find its degree. You have to look at this in standard form first. So negative 3x squared plus 2, and then you notice that the degree on top is 2, the degree on bottom is 2, so that's why down here in the horizontal asymptote space we just simply do the ratio of those leading coefficients. So the ratio of negative 3 to positive 1, that would just simply be a horizontal asymptote of negative 3. And something nice that happens here is that when you set the polynomial in the denominator equal to 0 and you solve, you're actually going to get some complex numbers. And because we're only interested in real number asymptotes, then we can just go ahead and conclude that we don't have any vertical asymptotes in this picture. And then example 6, this will be the last one that we do here in the video. It's a little bit of an application problem. So here they talk about an application problem that you can go ahead and pause the screen and read through if you want. But this is going to be a function right here that relates an amount of time spent in the sun to how sensitive your skin might be. And so they just ask us a couple of questions in this vein right here. So it says, find the amount of time a person with sensitive skin can be basically in the sun at these 3 times right here, right? So S is equal to 10, S is equal to 25, and S is equal to 100, right? So with those skin sensitivities, this is just an example where you just simply have to plug these inputs into the function and get their corresponding outputs, which you can see that I've done right here. Just don't forget that whenever you're doing a practical application problem, these are going to be something that you can dip back into the context and say, I've got this many hours, right? So that's something I expect you guys to be able to do. And then it says for part B, what is the horizontal asymptote of this function and what does it represent? Well, if you look back at the function formula here, you notice that the degree on top is simply just going to be a1. The degree on bottom is simply going to be a1. So we have equal degrees, so we know that the ratio of the leading coefficients is going to be equal to the horizontal asymptote here. So the leading coefficients here are simply just going to be the 0.37 and 1. So if you simply take the ratio of those, we just simply get 0.37. And just kind of interpreting that in the context of the problem here, it says no matter how high the UVB rays get, only 0.37 hours, which is going to approximately turn out to be about 22 minutes, is the minimum amount of time before you're able to get that sunburn, right? So again, whenever you're doing these practical application problems, it's just a matter of kind of thinking about how you would dip it back into the techniques that we've demonstrated here in this video. So anyway, that's going to do it for this one. Thank you very much for your attention. If you guys have any questions whatsoever, then please, as always, feel free to let me know. I'm going to be hanging out in the chat during our classroom time today, so feel free to go ahead and see me there. But thank you very much for your attention, and I'll speak to you in the next one.